Oh, well, you're recording.
Oh, I'm recording. Okay. Is that fine if I record this, or you want me to record it?
If you record it, as long as you send the video to myself and Dr. Trom, it's okay. We just
Okay,
want to
sure. I'll
have it
do that
for
right after
archival
this.
purposes. So, all right, cool. Well, then I'm going to go ahead and let the Bionic Builders take it away.
Hi, we are Bionic Builders, the shaker system for your microbioreactor. Our team consists of James Acosta, Shin Hai, Rachel Heinlein, Eric Lee, Devendra Ramdi, Colby Ross, Moksha Raval, and Heian Wang. Next slide. So in today's presentation, we'll go over the hedgehog concept, key features, design, evolution, cost analysis, and conclusion. Next slide. So our goal in developing our design was to create a reliable product with fewest number of manufactured products and simple to use. Next slide.
So here are some key features that are important to mention. We have a intuitive user interface, comprises up of 4 color-coded buttons to allow for an easy drop-down menu. It's a simple mechanical structure. It's comprised of approximately 24 parts, easy to manufacture, robust and manufacturing drive system. This is very similar to the Ultimaker S5 3D printer that's currently on the market today. It's been proven to work, and it has a compact size and ergonomic design to allow it to fit into any bioreactor on the market today. Here are some specifications. We have it being driven by 2 12-volt NEMA 17 stepper motors. It's approximately 10 by 10 by 6 inches overall in diameter or in size. Product weight approximately 5.5 pounds. The controls are digital, speeds between 10 to 350 RPMs in 5 RPM increments. Time setting is up to 99 hours, and you can set that into either 1 second, 1 minute, 1 hour steps, excuse me. The user is allowed to view an LCD display that's approximately 1.5 to 4 inches. It's a 4-line display. Max load capacity is approximately 2 pounds. We haven't went through the testing for this phase. A lot of the support for this is 3D printed currently, when it should be manufactured, milled in aluminum. Shaking patterns, linear orbital, double orbital, linear distance, orbital diameter, double orbital diameter, you can see here as per customer requirement.
So the design and artifact. So here you can see 3 different, sorry? Right. Here you can see 3 different photos from our final design that we prototyped ourselves in the lab. On the left, you can see the mechanical design that comprises of the 2 motors, and then there's the whole suspension system and everything. On the right, you can see the control box. It consists of 4 major buttons. One's red, one's white, one's yellow, one's blue. In the middle photo, you can see that they're labeled by color with the first letter of each color name. And it has an emergency stop switch on the bottom right and 2 LEDs. One's green to show that power is on, and then the red one is used below it to indicate an error, which we'll show you shortly. There's also a liquid crystal display, as mentioned previously. It's blue lit, backlighting, and you can see it there in the middle photo turned on with some text on it. All right, next slide. So, okay, yeah. It's a bit laggy, unfortunately, but here you can see a demonstration of the different types of orbital patterns and also the centering process that the device is capable of. So on the top left, you can see it performing a linear orbital pattern. Well, in this case, it's just linear motion. It travels along a diagonal for the total orbital area because, as simple geometry tells you, the hypotenuse of a triangle is typically its largest side, or not typically, it is the largest side. So by traveling along a diagonal like this, it maximizes the available distance that can be traveled in the linear pattern so that it has more modularity in your settings. The orbital pattern, as you can see on the top right, forms a circular pattern within the orbital area. It was coded using a series of different cosine sine function equations which were further extended to be used in the double orbital pattern, wherein once one orbit's complete, it switches the X direction motor's equation instructions to a negative instead, and continues the Y as if nothing had changed, so that it creates a figure 8 pattern. In the bottom right, you can see the centering process. So before any type of orbital pattern is formed, before you even start setting up what type of orbital pattern you want to do, the device will center itself to the middle of this orbital area. That way it can take full advantage of all of the area available to it. Next slide, please. Here you'll see a demonstration of the GUI. Again, it's a little bit laggy, which is kind of unfortunate. It starts off with it turning on screen, and then it centers itself, and then it shows you the first main menu. Then you get to toggle in between different radius sizes. The 3 different ones are all in millimeters. Then it'll show you the RPM setting. It increments by 15. You select it with the red button on the right left, and the blue button increments it. And then you can set the duration for how long you want it to run for. It goes in seconds, minutes, and then hours. And then in the bottom right, like it just showed, there's an emergency stop on and off switch, which toggles power. Next slide. Here you can see the 2 different types of error codes that you might bump into while operating the machine. So on the left is error code 1, which occurs when one of the limit switches on the outer bounds of the orbital area is actuated. And this is in order to prevent the machine from essentially ramming itself into a wall. So once it exits the appropriate orbital area, the limit switch will actuate, and it will bring up the error code and cause a system reset, essentially, wherein it stops all operation no matter how much time has passed, and it will begin the centering process again and bring you back to the main menu, and you must reset up your orbital pattern. This is to prevent damage to the machine. As you can see, the red LED is also turned on, and it turns itself off after the centering process has been done because the error has been troubleshooted. On the right side, it's a more serious issue. If, as occasionally seems to occur with the hardware that we have soldered, the motors are no longer responding to the Arduino that we used, then error code 2 comes up, wherein the process failed to more or less realign or actuate properly, and it needs to be turned off. The circuitry needs to be addressed because there is an issue. The red light indicates by blinking instead of just remaining on for this one. And the code essentially traps you within a while loop that will not continue progressing until you power off and power back on. All right, next slide. We'll now get into the design revisions that came across as we went through the project.
So firstly, I want to talk about the Kohler design. So Kohler is the essential mechanical part in this design, which can let the shaping table move with the build. So we have totally 4 designs through the whole semester, as we show on the right-hand side, 1, 2, 3, and 4. So the first design is to use the specific build with teeth and design the Kohler with corresponding teeth. We have the guided rail that pass through in 2 directions to let the shading table move with this Kohler. And the second design, the only differences between the second one and the first one is we use a normal guide rail with bearings instead of as the threaded rails in the first design. We'll talk about the guiding rail in the next page. The third design is using the belt clamp and use the belt clamp and the fixing screws to fix the belt with the Kohler. This is the current design and the finalized design. And the fourth one is we use we design specialized grooves that can let belt be pressed in the Kohler. This design is not as stable as others, as we discussed. So then we do not use the force plane. Next slide, please. Yeah. So we're talking about the final design. We have designed a kind of build clamp, which was composed by the build plane itself and 4 fixing screws. We have put belt clamp, screws, belt, and the Kohler as a sandwich style combinations. And this kind of design was proved that can fix the belt move was a collar really stable and robust. Okay, next slide, please.
As for the driving rod design, you can see some of the concepts we were contemplating on the right side. Design 1 utilizes a gear and belt to move the center block in one direction linearly with a ball bearing inside of the collar to allow for smooth translation. Design 2 was a simpler version of design 1 where we removed the ball bearing and collar. And then design 3 was the most similar to our design, where we would use a support and rail props to move the support structure, which in turn moves the center block. Next slide, please. So the design that we selected combined aspects from design 1 and 3 in the previous slide. So the collar holding the rod in the center has a ball bearing inside, which allows for smooth translation along the rod. Originally, the ends of the rods were to be threaded and secured using a nut and washer. However, due to the lack of manufacturing capabilities provided to us, the rods were secured using a press fit. Next slide, please.
This slide shows the evolution of the center block design as we progressed in our project. The first change that was made is we decided to attach the support blades across the hypotenuse of the center block, which you can see in the second design. After testing was done, we decided that the support plate needed more support, and we decided to make the center block wider to minimize the vibrations and just create a more sturdy design. We also decided to make it a little bit taller so that when the radius was set to be larger, there was no interference with the motors. Next slide. This slide shows how the center block is attached to the supporting blades and the ODFI plate. The supporting blades press fit into the center block, and then a set screw is set between the ODFI plate through the supporting blades into the center block. Next slide. During our milestone 2 review, we were told that our supporting plate was a little messy looking and way too large, so we made lots of changes to this. The first thing we did was minimize the amount of screws that we were using. This just makes for a cleaner design, and the assembly time is less as there are less components to screw in. We also minimized the size of every component in our design, and this allowed for the supporting plate to be minimized by a total of 7 inches, which overall is a better design as we were way exceeding the requirement, and we will use less product and time in manufacturing this way.
Okay, so moving on to our finalized design. Here's a CAD representation, which includes all the 3 main design modifications made throughout the semester. First, in the isometric view on the left, we can see the extrusion in the ODFI support platform, as well as the weld plate platform. And the motive behind this modification was to allow for easy placement and removal of both structures. And in the middle, we have 2 side views. In the top side view, we can see the revised center block supporting the weld plate and ODFI. As mentioned before, the center block was made larger in cross-sectional area as well as taller in height when compared to the original center block design to minimize interference between the motor support brackets and the ODFI platform. And the side view on the bottom, you can see the collar, which is modified in terms of its height, which was increased to prevent sagging in the belt, as well as getting rid of interference between the belt and the limit switch mounting screws, which led to unwanted friction within our system. Next slide, please. And here we have an exploded view of our support plate assembly, which involves everything other than the ODFI plate and weld plate supports. And here we have the screws for the belt clamp itself, the timing belt and pulleys, the collars mounted to the driving rods, as well as the base plate supporting bracket.
So since part of the customer requirements was to make the device easy to assemble for the user who purchases our device, we did perform a Boothroyd Dewhurst, and I may have pronounced that wrong, and I'm sorry, handling an insertion chart in order to estimate the amount of assembly time that would be taken by an individual who has no experience using our device. We broke it down into 19 different steps, which are outlined inside of our FDR, which can be provided to anyone who's interested if they asked by one of the professors. Your total assembly time came out to be about 17 minutes and 47 seconds. Next slide.
To conclude, we made 3 major changes that important to our system function over the whole design process. The first one is we redesigned the shaking plate, make it elevated, make it fit to the ODFI. The second major change is the height of the center block. We increase the height to make sure the center block no interface with the other parts of our system. The last major change is the height of the coder. Also, we make the increased height of the coder, make sure the belt is flat with the motor. Next slide. To test our system, we made 3 tests according to the customer requirements: linear pattern, orbital pattern, and double orbit pattern. All 3 shaking pattern can run at 350 RPM for at least 20 minutes. Actually, we did it longer. For linear pattern, we did like 1 hour and 30 minutes. For the orbital pattern, we did the test for 1 hour. And for the double orbital pattern, we did it for 45 minutes until we accidentally turned off the system. Next slide.
Okay, so we estimated the cost of individual machine for prototyping and manufacturing as 100 units. So left-hand side is the prototype cost summary, and the right-hand side is production for 100 units. As we can see, the prototype cost, we have totally cost of $620, and the production as 100 units at $608. Those costs are estimated by from the ODS part and the raw material purchasing, manufacturing, energy costs, and shipments and tax. So overall, our design, the cost is affordable and have enough profit space compared to other current design and products on market. Next slide, please. Okay, thank you for joining our presentation. That's all about our presentation and design. Please feel free to ask any question if you have.
Alrighty, guys, thank you very much. We'll go ahead and open the floor up for questions from our sponsors first.
I don't know if that was for me, but
That was for you. Go for it.
good job, everyone. This was a very well put together presentation, and I really liked your 90-second pitch as well. Very unique. Yeah, I have a general question about your experience with this whole project. Like, if you were to redo this whole process, what would you do differently? Whoever wants to go for it.
I can speak a little bit. One of the major shortcomings or issues that we had going through when we were actually manufacturing the mechanical design was that we had a lot of issues with the way we toleranced a lot of our fits. So if I could go back, I would have probably just reviewed them a bit more so that we didn't have to send stuff to be remanufactured multiple times. And it would have saved a lot of time in general.
Time and cost, right?
It's much further if we started over, just because we now work so much better as a group. We found our strengths and weaknesses. Instead of everyone trying to come together on one particular thing, we can now divide everything up efficiently, where we can rely on each other to get everything else done in a timely manner. That's my 2 cents.
But we could have also, now that we know what works, you see how in our design, some of the 3D printed parts aren't color coded. Some are purple, some are black, some are red. It's a minor thing, but we could have all made them one color.
Yeah, I guess just to add on to that, I mean, if assuming that all the parts were to be manufactured in the desired materials, we could have possibly changed our design, or maybe design for 3D printing rather than for aluminum manufacturing or any other material we had chosen, because that would have maybe changed our design, and maybe we could have made it more compact or more ergonomic in that way. But that's kind of was a setback throughout the semester, where the materials were kind of, you know, questionable was the outcome of how the materials were going to end up in our final design.
Yeah, all great insights. That is all for me, Dr. Nimi and Dr. Flynn, so.
Thank you. Dr. Trom, did you have any questions? I noticed that you managed to make it to the presentation.
No, I'm okay. I'm driving, so I don't want to be too distracted.
Okay. All right. Cool. Well, yeah, I guess, and pardon me if I missed it. I did have to step out for like 2 minutes there to put out a fire of my own. Metaphorical fire, not actual fire. The lab is still safe. It's not burning down, in case anybody was worried. So if memory serves, you guys had some migration issues. Did you figure out a solution for them? Am I thinking of a different group?
You might be thinking,
Sorry, you said what type of issues?
Migration, where it was slowly creeping.
Oh, like drift?
Yeah, drift.
Yeah, so I mean, we kind of diagnosed that the issue was mostly a result of vibrations. Typically at higher orbital speeds, there's like a lot of vibrations due to the motors. It's just how it is, I guess. We feel like a big part of that might be that the material is currently made of 3D printed parts, which has a lower stiffness than the aluminum would have, I would imagine. So it might be reduced in general if they were made of the proper manufactured material.
So I guess I'm gonna have a nice follow-up question for you guys then. If you were to redesign these parts, knowing that they were going to be 3D printed, what would you change about them to get them to have the stiffness to prevent those vibrations?
I feel like one big thing would be a higher infill.
That'll do it. Any other ideas?
yeah, I had for the collars, they're not secured in the way that I like them. Like they're only secured on one side, the way the fastener is. We need another set screw on the other side to prevent torsion of that collar. I feel like that is where a lot of the vibration comes from and a lot of the friction. So that's going to cause deflection in the overall system itself.
Sorry to interrupt the topic, I guess, but one thing that I also suspected might have been adding to the drift might be that the motors might just be skipping steps occasionally, which might be a torque issue or just a general coding, like not even a coding issue, just a hardware occasional mishap that you can't really adjust for. So maybe buying higher quality motors for our design and probably at a higher torque would maybe help remedy it. But that would require like prototyping and testing to determine if that's actually something that helps, because I'm not really sure.
Is it the motors or the motor drivers that would be for torque?
We tested the motor drivers and we tried setting that set screw to find that perfect point, but we just ended up mix matching the motors where they were running at different, I don't know. It could have been the drivers.
Well, so I guess we're now getting into fun stuff. You go and adjust a driver, so you're able to flow more current through that one. So I guess it's kind of like you turn on one sink in your house. full blast. What happens when you turn on the second sink? And then you turn on the bathtub, and then you turn on, and then you flush the toilet. Eventually, water pressure drops. So is there the possibility that you were just maxing out your power supply?
It is very possible. We spent, I think, like an hour or maybe 2 or 3 hours, honestly, kind of changing out different configurations for the amount of circuit or current that was allowed through the drivers to see which one would work the best. And at lower current levels, it was a lot quieter. The movement was a little bit more stable, I guess you could say, but at higher RPMs, it no longer performed as expected, as it wasn't, I guess, able to keep up with the code and what it required. And you know, we don't have a way to dynamically change this amount of current going into the system while we change the RPM levels. Otherwise, that would be ideal. But yeah, it wasn't able to perform at higher levels because of the low circuit, low current. But at higher currents, it worked a lot noisier and probably with the wave conditions, but it worked. So
Yeah, it was trying to find that sweet spot. It drifted regardless. If it wasn't enough, if the motors didn't receive enough, it drift. It received too much, it drift. So it was kind of in the medial.
All right.
drift also wasn't really a huge issue at small orbital diameters or linear sizes. Actually, I don't even think linear drifted at all. I don't remember it ever doing that. But like at larger orbital radiuses, it started to drift. But at small ones, you can run it for like 2-3 hours, or at least that's what we kind of got, about 2 hours for the orbital one. And it didn't really drift at all.
Cool. Good. Do we have any other questions for?
About the score sheet, do I send it to you separately?
Yeah, you can either email it to me or you can email it to Dr. Trump. So email it. If you need my email, well, actually, we'll go ahead and do this.
It should be up here too, so I guess.
I'm just gonna drop Dr. Trom's email into the chat. So you can send it to him. He's the one who's been collecting all of them. So yeah. So also send Dr. Trom a copy of the recording, please.
Yeah, sure.
And so yeah, with that, congratulations, guys. You're done. You're free. You have, if you're graduating this semester, congratulations. If you've got one more semester, hopefully I'll have the opportunity to see you all around a little bit more. And yeah, thank you again for a great presentation. And thank you to Michelle for coming and supporting the class. And yeah, have a great afternoon, guys.
Thank you.
Thank you.
Thank you.
Take care.